So hello everyone, my name is Pratham Kumanta. So we are gonna learn today how ultrasound travels from one medium to the another medium, or how ultrasound travels in a certain solid compact material. So let's go to the copy so that we can see details. So let's go. So let's go. So now we know that sound has a medium. Okay, sound has a medium. So here sound, as we all know that in ultrasonic testing we use ultrasound as a medium. So there are three zones where the sound travels. So there are three zones. So this is known as the dead zone, and this is known as the near zone. This is dead zone, this is near zone, and this is far zone. So here this and this is also a probe. This is a probe. Okay, so here in dead zone it means that in cathode ray tube we know that if a sound travels, then certain value it will show. So this value is known as the initial pulse. Okay, so in initial pulse the dead zone is situated. Okay, so in here the dead zone is situated where the initial pulse starts. So in near zone means in between the back one. So near zone means it is the distance between the initial pulse and the back valve. So this is called as near zone. So we know that from the dead zone where the initial echo pulse is situated. So this is the initial echo pulse. In near zone the sound fluctuates. So if there is any defect in near zone, so let's take an example. Here is a defect. Okay, so if the defect is situated in the near zone, so we cannot detect the the defect. Okay, sorry, my mistake. We can locate the defect, but we cannot detect the size of the defect. Okay, we cannot detect the size of the defect. Okay, because in near zone the sound fluctuate. In near zone the sound fluctuate. Okay, so for this phenomenon we cannot detect the size of the defect. Okay, so now there is a way to detect this defect, which is if we use the TR probe, then we can detect the size of this defect. Okay, so it is the same phenomenon as the angle of divergence. Okay, so it is the same phenomenon as the angle of divergence as we studied earlier. So from this theory we concluded that the near zone, the formula is d square f by 4v. So d square f upon 4v. So d is the diameter, f is the frequency, and v is the velocity of ultrasound. Velocity of ultrasound in that material which we are gonna inspect. Okay, so the velocity is the ultrasound that travels in the material which we are going to inspect. Okay, so from here we concluded that if the diameter of the probe is bigger, then the near zone also have bigger value. If the frequency is bigger, the near zone is more. Lower the velocity, bigger the near zone. So it depends upon vice versa. Okay, so now let's go to beam spread. So what do you mean by beam spread? So now we're gonna discuss about what is beam spread. It is same as the angle of divergence. Okay, so we know that beam spread means it is same as angle of divergence. So if the beam spread is big, then the sound travels in a short distance. It means that if a sound travels in this is the sound. Okay, this is the sound. So if the beam spread is larger, okay, so this is the width of the beam spread. So if the beam spread is big, then the sound travels will short. So it have shortest distance. And the beam spread is high, if the beam spread width is more, then the sound will not travel because of the loss properties of the sound, like attenuation. So if the sound has if the sound have a small beam spread, if the sound have small beam spread, here if the sound will have a lesser value. If the beam spread is less, then we have a clear cut value of the ultrasound. Okay, so this is the phenomenon. In sound, the parameter is used as dB, decibel. Okay, so we know that from the beam spread formula as kV upon sine theta by 2 is equal to kV upon df. So here k is a constant. It depends upon the material of the angle. So so here k, the edge of the k value will be 1.22. So it have a different value upon this angle. This angle it will have different value of a k. So here k will be 1.08, here k will be 0.56, and not this one, sorry, this is the beam axis, which is 0 degree. So here the value of k will be is equal to 0 because this is a neutral axis. Okay, so we concluded that if the value of beam spread is bigger, then the beam spread will be smaller. If the frequency is smaller, then the beam spread will be big. Okay, so that's all for today. Thank you.